So, thanks Adam for the presentation, and thanks for the opportunity to be here to present what is going for us to be, let's say, an intended work that we are planning to do in the future. Before moving on with the presentation, I don't know why it's going on automatically. PowerPoint is just making things. So I just want to point out that this work is part of an European project that has been funded by the Kistera scheme, and is about the study of in-hand manipulation. And therefore, when we have read the call for this workshop, we have been immediately interested by the application that this could have in our particular, of course, study. So I just try to give a small, in the presentation, I try to give a detailed, let's say a detailed description of what we want to do and why. So we want to study the manipulation, of course, and the manipulation is a complex task that requires the integration of different sensors, such as vision, touch, and proper perception. So we know that humans are effective manipulators. Actually, basically all what we are doing right now in robotics is trying to mimicking and perfection what actually humans can do, especially in terms of flexibility and their capability to generalize over different kind of manipulations and manipulation context. So, of course, the capability of the humans comes from different perspectives and are characterized by different sub-capabilities. And these capabilities and this peculiarity of the humans as manipulators have been used to inspire the development of specific grippers. We have actually nowadays more than 20 years of research on robotic hands, further studies about perception system, more complex perception system for the manipulation, using tactile sensing, using vision, using torque force sensors has been done, and especially a particular attention has been given to the usage of learning in order to be able to generalize over different tasks. So when we talk about learning, of course, we talk about machine learning, and in particular, in the last years, the development of deep learning gave a huge boost to in specific scenario, in particular, for example, in computer vision. But many different learning techniques have been used during the years in order to learn from human demonstrations in different contexts and different scenarios. But of course, machine learning approaches necessitate of well-designed and representative data sets to be able to be applied in real-world scenarios. And we think that the NIST-ATB benchmarks, well, we have focused our proposal now on the number one, but of the benchmarks, but of course, even the benchmark boards could be thought to be an interesting application scenario for what we are proposing. Actually, they represent an interesting tool in order to collect a human demonstration dataset, since basically they represent a challenging scenario of assembly, disassembly, in the case, of course, of the NIST-ATB #1. And most importantly, they already represent a benchmark. And this makes possible either to ask other researchers to contribute to the dataset, enlarging the dataset and having, of course, larger dataset that we have pointed out is a critical point. And especially, it gives us the possibility then to test let's say, the results of our machine learning and application, and of course directly on the robotic application, since this benchmark has been studied for this specific purpose. So, as I was mentioning before, our objective is to develop an experimental setup that gives us the possibility to collect a data set of human demonstrations for human manipulations. In this case, we are focusing mainly on the NIST-ATB benchmark. So I want to point out which are basically the components that are going to interact during the experiments of the human demonstration. Well, the components that we want to observe are the human hand, of course, and the object. The human hand is a quite complex, has a quite complex mechanical structure that, generally speaking, can be resembled using a 26 degree of freedom model. And of course, for what regards the human hand itself, it is able to provide a tactile feedback to the person. On the other hand, the object, in order to be described, we need a 6 degree of freedom. Technically, in case of, in other kind of scenarios in which the object has an internal degree of freedom, we could need more degree of freedom, since I'm thinking stuff such as a book that can be opened. But in the specific case that we are considering right now, we are going just to limit our description to a 6 degree of freedom, so position and orientation of the object in the environment. And of course, it is characterized as well by the shape, the weight, and the stiffness of the object. So our experimental setup is composed basically from 3 sources of information: a data globe, an RGB-D cameras, actually more than one RGB-D cameras, and the motion capture system, a marker-based motion capture system. So here we can see a picture of the data globe. Actually, this is a preliminary version, and we are right now working on a second version that is going to integrate tactile sensors on the fingertips as well. But basically, the data globe has 12 9-axis IMUs. Is going to have at least six FSR, one for each fingertips, plus a set of FSRs on the palm, at least one, but probably more, and the 14 reflective markers that are needed, of course, for the motion capture system to work. All the sensors are connected to a microcontroller unit that sends the information through Wi-Fi to the computer. The kind of information that are generated by this data globe are, of course, the data collected from the IMUs. So for each link to which the IMU is connected, we are going to have linear acceleration, angular velocity, and since we are talking about a 9-axis IMU, we have the magnetic field direction as well. And of course, since we are planning to have force resistor sensors on the fingertips, we are going even to have some contact forces in some specific places, not force all over the globe. From this information, the image just cut out a piece of the text. So from this information, we are able to derive some more high-level features, such as the hand joint positions and the kinematic information, as well as the tactile information. For what regards instead the motion capture system, we have built a small motion capture cage that hosts up to 8 infrared cameras. And the cameras, actually right now the layout of the cameras has changed slightly, so that is able to cover all the space better, let's say, all the space. And the kind of information that we can, the data generated by motion capture are 3D positions of all the markers. And this information can be used to derive other features such as the end joint position and the end poses. So there is a bit of redundancy in terms of data. We have either the motion capture system and the data glove that are able to provide us the joint angles. The idea is to try to validate our data glove in order to be able to perform experiments even in a less structured environment. Then, of course, we have the cameras. We are planning to use RGB-D cameras. Right now, we are using Kinect, but we are planning to move to Z2 cameras. Anyway, cameras that provides either RGB images and point clouds. And of course, there are different software tools that can help us extracting information such as the end pose, the object pose, and the kinematic information of the hand as well. So for what regards the experiment, we were thinking that we need at least 20 volunteers in order to have to start having a data set that can be meaningful for people to work with. And of course, following even the recommendation of the guide of the NIST-ATB kit, the idea would be to consider different scenarios in which the person should assemble or disassemble the kit. And of course, in the cases in which the kit is disassembled, the idea is to have all the objects, all the different parts in randomized positions at every time. So basically, the idea is that this dataset can be used either to study the human hand kinematics, so that a robotic hand could be able to manipulate in similar way the parts that the user is actually manipulating. But at the same time, higher features can be learned and can be extracted, such as the order with which specific parts are picked, so the order of the assembly task. And at the same time, since the particular task is a challenging task and a challenging scenario, the data set could be used in order to train more advanced machine learning methods in order to detect the objects, recognize the object shapes. Is particularly difficult because in most of the scene, actually the person will have their object in hands, causing occlusions. And of course, again, from a computer vision perspective, the recognition of the human hand postures can be explored as well. For what regards the collected data set, as we have seen, it will contain all the source of information that we have mentioned before, and we are planning to make this data set publicly available. And of course, as I was mentioning over the presentation, this is, let's say, an idea that we came out as a challenging scenario to explore human manipulation, but we are actually designing this in order to be flexible and modular scenario platform to study the human manipulation. So new sensors and different sensors, of course, could be added in this scenario according to the feedback of the community, and different application scenarios that maybe does not directly involve the NIST-ATB one board could be considered as well. And thanks for the presentation. Well, there is just an interview.
Thank you very much. Does anybody have any questions for Alessandro? Cindy.
Hi. I guess a couple of thoughts. So we've been doing human manipulation, like using humans to do manipulation tasks and seeing what they do. We've been using robotic hands, so we've been using robotic hands as a proxy, so it's a little bit different. But one thing we really found was that when it comes to low-level manipulation, like here, move this object to here, from here to here, people are surprisingly consistent. So yeah, if you look at a whole task from end to end, like, you know, making a sandwich or something, there's a lot of variability. But when you get down to the level of like, pick this up and put it in here, you may find that you don't need 20 people because everybody does it the same way. So that I was just going to say that 20 people may be more than you really need for if you have lower level tasks, like pick up a screw and put it in. I guess one of my questions is, what tasks are you looking at doing, and is your intention to understand how people do these tasks, or is your intention to collect data that can then be used to drive how robots do things?
Well, so let's say that everything starts from the European project that I was mentioning at the beginning of the presentation. Wait, I just moved this here so I can see you while I'm talking. And so the main idea of the project, which basically we are, as a partner, the one in charge of collecting the data sets, is to explore the human manipulation, to understand how humans does specific complex manipulation in order to be able to replicate this kind of manipulation in a robotic platform, in let's say a robotic hand. The idea here, let's say that is to use a similar setup respect to the one that we are using for the project, but in a slightly different scenario, in which basically is respect to the kind of scenarios that we are going to consider in our project. This is a more complex scenario because we are for now just thinking about rotating blocks in hand, this kind of tasks. Here there is probably for what regards the manipulation, dexterous manipulation in the NIST dataset, there is not much, because probably there is not necessity to change the configuration of the object of the part once you have picked it. But there is, let's say, it's more difficult in terms of perception in order to be able to see all the different parts, because are particularly small, and even shapes that are not that even in some cases the shapes are not that different between themselves. So let's say that this is our perspective. And to answer your consideration, probably you are right. we were even considering, I mean, our idea is to try to consider different initial poses, different in terms of poses of the objects, and not only let's say the 3D position, but even the orientation. So different orientations could result in a richer data set.